Good morning. I am Leonardo Trujillo. I am going to present the work entitled Simulating Short and Long-Term Evolutionary Dynamics on Rugged Landscape, which has been done in collaboration with Paul Banse and Guillaume Beslon at the French Institute for Research in Digital Science and Technology. In evolutionary biology, punctuatory equilibrium is a theory that proposes that once a species appears, the population will become stable, showing little evolutionary change for most of its history. This state of little or no morphological change is called stasis. So, extended periods of evolutionary stasis are punctuated by rapid transition between states. On the other hand, on the other side, punctuated equilibrium is contrasted against phyletic gradualism, a theory that proposes that evolution is uniformly and steady with gradual transformation. To present the problem that we decide to attack, we can do so by citing the following text from a key article on this topic published by Ujeda and collaborators. We lack a comprehensive understanding of evolutionary pattern and process because short-term and long-term data have rarely been combined into a single analytical framework. Understanding in a single framework, and so the challenge is understanding short-term and long-term evolutionary process in a single framework. Our purpose is to simulate that on rugged fitness landscape. To clarify what we mean by rugged landscape, let us quickly recall that the fitness landscape is a metaphor introduced by Wright in 1932 to describe biological evolution as exploration through a subset of a genotype space, driven by successive mutation and constrained by environmental fitness selection. It is assumed that the landscape is shaped by the epistatic interaction between mutation with high fitness peak separated by valleys of low fitness genotypes, where the altitude is proportional to the fitness value. In this framework, one can model evolution as adaptive walls over the fitness landscape, where points represent population driven by mutation and constrained to selection. A very convenient approach is to study the evolution of a single initial genotype and its successive mutation, which correspond to the regime of a strong selection with mutation, which model the evolution of a monomorphic population. However, there may be a problem, which is that once a local maximum of fitness is reached, evolution becomes stuck and cannot continue exploring other higher fitness, or even never be able to reach a global maximum. Some theories have been proposed to understand why evolution does not stop, such as, for example, the valley crossing, the stochastic twin. In the metaphor of the fitness landscape, this can be interpreted as a jump that allows to escape from a local peak, say through simultaneous mutations in a single evolutionary step. Sure, it is not easy at all to conceptualize in a single framework micro and microevolution. However, we are convinced that one aspect that has been overlooked is how evolution at the molecular scale can be implicated in the time scale of evolution. And therefore, our proposal consists of taking a look at the molecular scale of the genome and the structural modification due to chromosomal rearrangements. In our model, we assume that the digital organism genotype is a circular binary sequence of length n So a possible genome combination define a hypercube space inspired by molecular biology. These genotypes are double-strand binary vector, where the complementary vector is defined such that 0 flips to 1 and vice versa. And from the biological point of view, we say that our model mimics the molecular evolution of circular viruses. Among the different chromosomal arrangement, we are particularly interested in inversion mutation because they conserve the genome size, which, for example, simplifies not having to consider change in the dimension of the fitness landscape. And for example, they are the second most frequent mutation in long-term evolution experiment, such as those carried out by Professor Nesky in his lab in Michigan. We model the chromosomal light inversion as a two-step procedure, conjugation operation, flipping from 0 to 1, and vice versa, and followed by a permutation operation. Mutation occurs between sites I and G, for example, which are drawn at random. And when I equals J, we have a point mutation or bit flip. And of course, we need fitness landscape. And for that, a well-known model to simulate artificial molecular evolution is the Kaufman-NK fitness landscape model, where besides the genome length N, there is a parameter K, which describes the episodic interaction between the sites in the genome and the contribution of each component of the total fitness, which depends on its own value as well as the value of K other sites. The most important feature of the NK model is that the parameter K tune the landscape ruggedness, that is the distribution of fitness local maximums ranging from non-epistatic interaction when K equals 0, single peak, to the full rugged landscape when K equal N minus 1. So here, the vertical axis represents the evolution time step of generation. Green dots represent clones of a given initial genome. We simulate adaptive work for each clone, each one, that is independent evolutionary trajectory for each clone. This is what we call a hike. Blue and red dots symbolize point and inversion mutation, respectively. We outline 3-time scale, initial transient period in which point mutation predominate, followed by a ecstasis-like period where the occurrence of mutation is very low or even null. Then a period that restart the dynamics, which is only possible if mutation by inversion occurs. So finally, the idea of evolutionary burst, which is roughly a succession of point mutation after an inversion occurs. Okay, now we present simulation for 100 hikes initialized with the same genome, which have length n equal 50, simulated on NK landscape with epistatic interaction, k equal 20 between sites, and the scatter plot here shows the evolutionary process with point mutation alone. The total final time per hike, that is the time when the last mutation has been fixed, doesn't even reach 10 times 3 generations, verifying that the hike stops at local fitness peaks. Let me point out that this simulation ran up to 200,000 generations. And this is what happened when we include inversion mutation with when the evolutionary dynamics last much longer than the case with bit flips or point mutations alone. So we say that it is the key finding of our work. There exist late mutational events which are driven by inversion mutations that allow the evolutionary process to continue far away on time. And therefore, we have verified our proposal that inversion are a mechanism, or could be a mechanism for escaping a local fitness peak. This can be better appreciated now, where the tail of the distribution of the final time per hike, okay, are larger than when inversion are lower than the case with point mutation alone. So the total number of generation when inversion are fixed can be almost 30 times longer than the total number of generation range when point mutation are the only source of genome variation in evolutionary dynamics. So now we can verify that the action of inversion can drive the dynamic to higher fitness value, showing that some, let's say that new fitness peak are discovered when inversion are lower. In the histogram, this corresponds to the beams of fitness between 0.68 and 0.74. So peaks that were previously inaccessible when the fitness landscape were explored by point mutation alone become accessible through inversion. So now we compare the behavior of the evolutionary dynamics with different values of the p-stability parameter, K, 2, 10, 20, up to 49. That is from a moderately rugged landscape to a full random one. We can see in the early stage of the evolution, point mutation predominate over inversion, the blue points, remember, the red ones are inversion. So this period lasts roughly from 10 times 2 to 10 times 3 generation, even though this is less differentiated for the full random landscape, K equal 49. Then for K equal to 10, 20, we can identify a gap of evolutionary activity, the stasis-like period that lasts approximately up to 10 times 4 generation. So some mutation occurred during this period, but most of them were preceded by inversion that took place early in the evolutionary process. Then from K equal 20, the mutations are more scattered than the stasis-like period tends to vanish. When K is large, the number of local fitness peak increase. Therefore, even when genomes are able to escape their current peak, it is likely they have only found a different local optimal rather than a global optimal. Therefore, science inversion only relays genome from local optima rather than finding global optimum. So, inversion mutation are less evolutionary efficient as K increase. Finally, we present a selection from the experiment presented previously of those events that can be identified as possible evolutionary bursts. Here we can see more clearly how inversion mutational events contribute to escape local fitness peak, especially in the case when K equal 2, where it is noted that the different heights quickly get stuck in local fitness peak. Once again, we see how the evolutionary dynamics reach a state of stasis, evolution being boosted again with the occurrence of an inversion after a long period of waiting time. For K equal 10, 20 and 30, the magnitude of the fitness increase are quite large in comparison to the case when K equal 2, which translates into a high step slope, giving the impression that the evolution process has not only been restarted, but also boosted. For the value of K equal 40 and 49, the stasis period has almost completely disappeared. And mutational inversion events occur at any evolutionary time scale. This is easily understood, saying the increase in the disorder of the now many fitness peak has an effect on the randomization of evolutionary state. When stasis is high, evolutionary dynamics is more turbulent, meaning that there are not well differentiated time scale between the type of mutation. So our conclusion Our model reproduced an evolutionary pattern alternating short and long-term time scale without resorting to a description at the population level. Despite its simplicity, our model showed that such pattern can occur in a stable environment through the sole intricacy of the different mutation operations having different exploration time scale, and our model could describe a simple scenario that nevertheless can shed light in punctual equilibrium and complex interlocking micro-macro evolutionary dynamics. So, take home message, and thank you very much.